Hi everybody, and welcome to my talk. Today I'm going to talk about simple virtual Skein theories. But before I do that, the work that I'm going to talk about was heavily influenced by von Jones, who unexpectedly passed away a few weeks ago, and so I want to dedicate this talk to him and to all of the work that he contributed to our field. So I think about virtual knots a bit differently than you all do. I should say from the outset that I'm not a knot theorist, and so if I say something incorrectly, it's because I approach these things from a more quantum algebra perspective. But essentially, I think of knot polynomials as a small portion of this larger object called a planar algebra. So before I can explain to you what a planar algebra is, we need to talk about what a planar diagram is. So a planar diagram consists of the following data. We're going to have one outer disk and some number of inner disks on the inside that are non-overlapping. We're going to have a finite number of marked boundary points on each of the disks. Connecting those boundary points will be a collection of smooth, non-crossing curves called the strings of the diagram. And the outer disk and the inner disk will have a starred region. So let's visualize this and look at an example. And so here we can see an example diagram. And all of these diagrams, by the way, are considered up to smooth isotopy. So a typical planar diagram might look like this. We see here that we have one outer disk and we have three inner disks, and we have some number of strings connecting to all of them. Notice here that it's possible to have a self-connecting string on either an inner disk or the outer disk. Each of the disks have a starred region. I call this the Emily Peters fundamental diagram, by the way, because this is from her dissertation, and pretty much anyone who talks about planar algebras just takes this diagram, and so I'm trying to reattribute the original credit to this diagram, which is from Emily Peters. So as it turns out, we can think of these planar tangles as the operations on a planar algebra, and these planar tangles will form an operad, and it's an operad under composition. So how do we compose two tangles? We can compose two tangles if the number of strands connecting to the outer boundary of one of them equals the number of strands connecting to the inner boundary of the other. So an example of this composition is here. We can see that if we take 4 and plug it into where 2 is, what ends up happening, we get a self-connecting string, and 2 is now replaced by 4. And again, this is up to smooth isotopy, so we can always smooth these out and make them look nice. And again, we call the set of isotopy classes of planar diagrams together with composition the planar operad. And so now that we know what the planar operad is, we can describe what a planar algebra is. So a planar algebra is simply a family of vector spaces together with an action of the planar operad. So as an example, in the previous planar diagram that we saw, a planar algebra would determine a multilinear map from V2 tensor V4 tensor V4 into V6. That also respects any composition like we saw on the previous slide. And some planar algebras will also have the following nice property. A planar algebra is said to have modulus D if inserting a closed string into a planar diagram just causes the multilinear map to be multiplied by some complex number D. And usually that complex number is non-zero. Finally, we also want to define what maps of planar algebras are. So a homomorphism of planar algebras is just a collection of linear maps from Vk to Wk that intertwine the two actions of the planar operad. And we will say that two planar algebras V and W are isomorphic if the phi k are isomorphisms. Often, we will draw planar diagrams in standard form. So we draw all boundaries, inner and outer, as rectangles instead of circles, where they're pulled parallel to the axes, and we orient each rectangle such that the sides have no strings and the left side of the rectangle is always the starred region. And typically, we put half of the strings on top and half of the strings on bottom, but sometimes for convenience, we ignore that convention. As an example, we can see here that we have the multiplication diagram. So you can see that multiplication in a planar algebra is simply just vertical stacking. As you can imagine, a natural class of examples of planar algebras come from tangles. And when one defines a ring or an algebra, we often want to describe it using generators and relations, and we can do the same thing with a planar algebra. And so we'll say that a planar algebra V is generated by a set of elements R if for every element of V there exists a planar diagram T such that T of some collection of R elements equals V for some Ri and R. In other words, a planar algebra is generated by some set R if every element of that planar algebra is the result of some arbitrary composition of diagrams from the set R. So when one studies all quotients of a Ringer algebra, you might instead think we could classify all two-sided ideals. And so we can do a similar thing with a planar algebra. So let V be a planar algebra. A planar ideal I is any subset of the planar algebra V such that I is the kernel of some quotient map of V. Equivalently, we can think of I as a planar ideal if it's closed under arbitrary composition with any element of the planar algebra. And so if V is a planar algebra, a Skein relation is just an element of the kernel of a quotient map from V. And a Skein theory is a set of Skein relations that generates the planar ideal. And in this talk, we will be relying on Skein theoretic definitions of planar algebras, which will be really reminiscent of knot polynomials. Our first example of a planar algebra is the planar algebra of tangles. And the planar algebra of tangles consists of vector spaces V2n for all n greater than or equal to 0. And we'll call these V2n the 2n boxes, and they're formal C-linear combinations of tangles with two end endpoints, which is just generated by the overcrossing. So clearly we can get the undercrossing simply by rotating the overcrossing. And we'll say that two diagrams are equivalent if one can be obtained from the other via smooth isotopy or the second and third Redemeister moves. So here we see Redemeister 2 and Redemeister 3. Note here that we are not explicitly requiring Redemeister 1 for reasons which we'll see in a second. Thus, any Skein theoretic knot polynomial can simply be thought of as a quotient of the planar algebra of tangles. Of course, one of the most famous examples of a knot polynomial is the Jones polynomial. So let's explore the planar algebra version of that, which we call the Temperley-Lieb-Jones polynomial. So the Temperley-Lieb-Jones polynomial is a quotient of the planar algebra of tangles, like we just mentioned, with initial box space dimensions 1, 1, and 2. And it's subject to the following Skein theory. So here we see that we can remove the circle by multiplying by negative a squared plus a to the minus 2. We have a twist relation, so we don't exactly satisfy Redemeister 1 here. We have a twist relation, which tells us that the twist can be resolved if we multiply by negative a to the negative 3. And then we also can resolve the crossing by setting the crossing equal to a times the identity plus a inverse times the cup cap. And this is called the Temperley-Lieb-Jones polynomial and not the Jones polynomial by itself, because if you think about it, the crossing resolves to the cup cap and the identity. And so really, this is just a polynomial with no strands in it, because we can always remove all of the strands. And therefore, it's really just the Temperley-Lieb planar algebra, if you're familiar with that. Of course, we can also define the Kaufman polynomial or any other Skein theoretic knot polynomial similarly. But what we're focused on today and what you all are focused on in this seminar is virtual knots. So let's define the planar algebra of virtual tangles, and then we'll get to what I've been working on with classifying small quotients of that planar algebra. So the planar algebra of virtual tangles has the same definition as before, except that we're adding a third crossing called a virtual crossing, which all of you all in this seminar are familiar with, but we're going to include that as a second generator in addition to the overcrossing. And from my perspective, I know there are a lot of different ways that you all think about virtual knots, but I like to think of it as just removing the planarity condition on the crossing. So now, if two strings want to cross each other, I just put a virtual crossing there. So now, as you know, we now have, in addition to the standard Redemeister moves, we also have the virtual Redemeister moves. And so here they are listed: virtual Redemeister 1, Redemeister 2, Redemeister 3, and then the mixed relation. Notice here that a priori virtual Redemeister 1 could be plus or minus if you work out the math, but it turns out that those two planar algebras are isomorphic to each other, and so we're just going to pick the plus case because it makes it easier for our calculation. Importantly, a non-relation that we're going to see is called the forbidden move. Essentially, we are not allowed to pull a string across a virtual crossing. And so we can see that this is not going to be a relation in general, but for some of these in our classification, it actually will be satisfied. So one more time, the planar algebra of virtual tangles is simply the planar algebra generated by the overcrossing and the virtual crossing, subject to the virtual Redemeister moves, which of course also includes Redemeister 2 and Redemeister 3. So what I did is I looked at certain small quotients of the planar algebra of virtual tangles. And what do I mean by small? I mean that I put some dimension restrictions on the low box spaces and then saw what possible planar algebras there could be from that. So first, I insisted that the zero box space be one-dimensional. If the zero box space isn't one-dimensional, the planar algebras already become incredibly unruly, and so we would have no hope of classifying them if the zero box space wasn't one-dimensional. And as a reminder, the zero box space is just the set of diagrams with no endpoints, and so you can think of these as your typical knots and links. And because the space is one-dimensional, that also includes the diagram, the empty diagram. And so in particular, this must mean that the circle is equal to some value times the empty diagram, and we call that value D. We would also like for the two-box space to be one-dimensional. And so in particular, remember the two-box space is just diagrams with two endpoints. And so in particular, this must mean that the twist is equal to some multiple of the untwisted strand. And so we should be able to untwist any twist in our diagram by multiplying by some value A, which is a non-zero complex number. The last and most consequential requirement is that we want the four-box space to be less than or equal to 3. So clearly, the four-box space is spanned by the cup cap, the identity, the overcrossing, the undercrossing, and the virtual crossing. And so there has to be some relation between those 5 diagrams. And so we're going to seek to classify all non-fully flat Skein theories with these conditions. And when we say fully flat, we mean we don't want the overcrossing to just be some multiple of the virtual crossing. So to be quite honest, the classification of these small groups was actually a lot more tedious than I anticipated. It involved a whole bunch of different things, including some representation theory, including some category theoretical arguments that I didn't really anticipate. So in this talk, we're not going to discuss how I arrived at the conclusion, but I will tell you what the result was. And so the theorem is that if I have a quotient of the planar algebra of virtual tangles with my following dimension restrictions, that is, that the zero box space and the two box space have dimension 1, and that the dimension of the four box space is less than 3, then the non-fully flat planar algebras up to isomorphism are the virtual Temperley-Lieb-Jones polynomial. So that's just the Temperley-Lieb-Jones polynomial where we also add in a virtual crossing, and a new one-parameter family of planar algebras called Repo2, and the value of the twist is given by some value A in the complex numbers. So I arrived at this classification following this flowchart. So first, if we take the cup cap and the identity, if they're dependent, then I'm just going to get a one-dimensional four-box space, which, if you think about it, automatically implies a relation between the overcrossing and the virtual crossing, which would mean that the planar algebra was fully flat. And of course, I don't want that, and so we're not going to consider that case. If the two are independent, then now let's ask the question about the identity, the cup cap, and the virtual crossing. If the two were independent, then we're going to get this interesting Rep02 case and the virtual Jones polynomial. But if the two are dependent, then in either case, we arrive at either a planar algebra that doesn't make any sense, that's contradictory in some way, or one in which it's fully flat. And so in neither of those cases do we get anything new. So one obvious application of these planar algebras is to find link invariants. If we think about the zero box space, we know that any closed diagram is a constant times the empty diagram. So in other words, every diagram, every knot or link resolves to a number. Therefore, we get a link invariant by just using the relations of the planar algebra. In this case, though, most of the link invariants are not new. we already know about the link invariant coming from the virtual Jones polynomial because Kaufman talked about it. And the link invariants coming from all of the other cases that are fully flat are just like -1 times the number of crossings. So they're very uninteresting link invariants. And a priori, this planar algebra, which I'm calling Repo 2 for reasons which I mostly won't discuss here. Of course, if you have questions, you can send me an email or put them in the comments and I'll answer them. This case that we're calling the Repo 2 case could, a priori, have a potentially interesting link invariant. So let's talk a little bit more about what that planar algebra looks like. So the Repo 2 planar algebra has the following Skein relations. So it has a circle parameter of 2, it has a twist relation A, and it has a crossing formula that is given by the following relation 6 here, where A is some non-zero complex number. And as it turns out, this interesting braiding is actually inherited from the circle group. You can write O2, the group, as a semi-direct product of S1 and Z mod 2. Interestingly though, this family of Skein theories actually does satisfy the forbidden move. And so I just used the previous crossing relation to get rid of the virtual crossing. And when I do this in both situations, I get the following two formulas. And you can see that the second and third formula are really equal to each other if you use Redemeister 2s and Redemeister 3s. And so we can see in this case that the forbidden move is actually satisfied. Since this Skein theory actually does satisfy the forbidden move, it actually implies that this Skein theory gives a trivial link invariant. And Kaufman sketches a proof for this link invariant and shows that it's given by the parameter A and the linking matrix of the link. For a knot K though, the invariant formula is simply A to the right of K plus A to the minus right of K. So unfortunately, the link invariants that we get from this classification are either not new or not exciting. And so for some of you listening to this talk, you might be a bit disappointed by the result. But the good news is that this was actually an exercise to a much harder question, which is the following. Before, we only allowed that the dimension of the 4-box space go up to dimension 3. But what if we expanded it to include dimension 4? In this case, it could be possible that we get some new and interesting Skein theoretic knot and link invariants. So one example of such a planar algebra that we know exists in that category is coming from the representation theory of the automorphism group of the Higman-Sims graph, which is just the Higman-Sims group semi-direct product with Z mod 2. And this turns out to be a very hard question. And the reason that this is a hard question is because we aren't guaranteed a Kaufman relation. That is, we're not guaranteed a relation of the following form for some z in the complex numbers. In addition to the Skein theories we talked about today, I also performed a similar calculation for oriented virtual tangles, and for Skein theories it also included a trivalent vertex. I would like to thank my advisor, Noah Snyder, for helping me with this process. Like I said, it was incredibly tedious, so his help was very much appreciated. Before we conclude this presentation, I just want to thank the organizers for giving me the opportunity to send in a video, and for you all for watching it. If you have any questions or comments, feel free to leave them in the comments below this video, or you can also email me and I'll try to respond to you as soon as I can. Thank you so much again for watching this video.